Hello everyone, welcome to Coders Camp. Today we are going to cover all elements in two binary search trees. So the input given here is head or root of two binary trees, and we have to return all the integers in both the binary trees in ascending order. So how are we going to approach this? So here is a given example, binary tree 1 and binary tree 2. This is pretty straightforward problem where you have to work on your skills on understanding the time and space complexity. So let's see how we're going to solve this problem in various methods. So the method 1 is having them stored in a single array. So we just going to traverse the given binary trees in any order you like in order, post order, or pre order. Let's say we are going to do an in order traversal and add all the elements in the array. So by doing so, the binary tree 1 will be having 10 comma 7 comma 4 comma dot dot, and then continuing to it, we'd be adding the elements from binary tree 2 also. So 5 3 2 4 6. So once all this is done, we are going to sort them using array.sort inbuilt function. So yes, this is going to work fine, but the problem here is the time complexity. So first to traverse binary tree 1, it is going to take big O of m. Let's say m is the number of nodes in the binary tree 1, and big O of n is the number of nodes in binary tree 2, and another big O of log of m plus n would take for the array.sort algorithm or method to sort the given array. So this is the overall time complexity of this method, which is definitely not going to be the optimal one. So how do we further optimize it? So the method 2 is again saving them in array, but not in a single array. Instead, we'll be saving them in a two separate array. So array 1 will be having the in-order traversal of binary tree 1, and array 2 will be having the in-order traversal of binary tree 2, and finally we are going to merge these two arrays and create another array which is in a sorted order. So what is the advantage of going from the method 1 to method 2 is to put uh, array 1 and array 2, it is going to take big O of m plus n time, and again to merge array 1 and array 2, it is going to take another m plus n time. So ignoring constants, the overall time complexity would become big O of m plus n. So this is quite an optimal solution compared to the method 1, but still we can further simplify it in a more optimal way by getting a clue from this problem statement. So here it is not given that we have to return a sorted two arrays or lists or something. The inputs are in the form of binary search trees for some reason. So we are going to get the help of this logic and going to optimize our solution. So let's see how. So for an optimal algorithm, we are first going to choose a data structure that let us insert and delete values in constant time. That will reduce a lot of our algorithm execution time. So we are going to have a stack 1 and stack 2, which is going to hold the values of binary tree 1 and binary tree 2. So the concept here is we are going to maintain a minimal stack, which is nothing but one. We are going to put the values on into the stack only if they are minimum than the top element. So if it is going to be maximum, then we are going to wait until it its position gets emptied. So let's see, let's start from our first binary tree, our root node. Root node is going to be the first node that we are going to visit and we are going to add. So let me add 10 to our stack 1. So moving on to our next value by in order traversal, the next value that is going to be traversed will be 7. So let's add 7 because 7 is obviously less than 10, and then the next value going to be traversed is 4. So let's add 4 next to it because 4 is again less than 7. So the next value which will be traversed in the binary tree 1 according to the in-order traversal is value 9. But if you see the top of the stack is going to be 4, so we have to wait till the position for 9 vacates, which means we have to pop 4, we have to pop 7, and then only we can insert 9 because 10 is the higher value than 9. So this is the position where 9 has to be. So we have to wait till our stack clears that position. So let's move on to our binary tree 2. Since we have done with our binary tree 1, the first value is going to be 1. So let's add 1 into the binary stack 2. And the next value we are going to see is 3. 3 is less than 5. And the next value is 2. 2 is less than 3. And the next value in order is going to be 4. 4 is greater than 2, so we have to again wait for our position 4 to be vacant. So now we have our stack with set of elements which are already in ascending order. So what we are going to do is we are going to merge them and put it into a list. So let's have a result list which is going to hold the values one by one from the stack. So now let's compare the top values of both the stacks. So 4 compared with 2 will give you 2. So now we are going to add 2 to our list first and pop the value 2 from our stack. So now the next value is going to be 4 and 3. So let's compare 4 and 3, that is top of both the stacks. The value is going to be 3 because 3 is lesser than 4. We are going to add that to our result and then pop that value from our stack. So now, before comparing the values 4 and 5, we keep checking whether any elements are eligible to enter into any of the stack. So if you see, the next element that is waiting in binary tree 2 is 4, and the next element that is waiting in binary tree 1 is 9. But 9's position is not vacant, but 4's position is vacant in stack 2. So what are we going to do is we are going to insert that position or value into our stack 2. Because we are going to maintain the overall elements in ascending order and then merge them together into our result. So now it's time to compare 4 and 4. So both the values are same. So let's pop it from our stack 1. So I'm going to insert 4 to our result. And then we are left with 7 and 4 for comparison. So in this case, 4 is again the lesser value. We are going to check what are the values left in both binary trees to be inserted into our stack. So if you compare, the next value that is waiting is 9. 9's position is still not vacant, and one more element that is waiting in binary tree 2 is 6. So if you compare 6 and 4, 6 is a larger value, so we cannot put 6 into stack 2 yet. So we are going to compare the top elements in both the stacks, 7 and 4. In this case, 4 is again a smaller element, so we are going to put 4 into our result. Again, we are going to pop it. So is there any element we are going to insert? No, because 6 is higher than 5, so we are sticking to the comparison. So next we are going to compare 7 and 5. Again, 5 is the lesser value, so we are going to update 5 to our result and pop that from our stack. So once it is popped, we are again going to check whether 6 can be inserted. Yes, 6 can be inserted. So we are going to insert 6 to our stack. So let's the comparison happen again. Out of 7 and 6, 6 is going to be the lesser element, and that is going to be popped from our stack 2. And now we don't have any other elements left in the binary tree 2 to insert to our stack 2. So let's stop the comparison and stick only to the stack 1. So now stack 1 is having 7 at the top. We don't have elements to compare, so we are going to put 7 in the next row. So now the 9th position is vacant since we popped 7 and added to our result. We are going to put 9 into our stack next. So now adding 9 to the stack, we don't have any elements to compare, so we are going to pop that as well from our stack and add it to our result. And finally, we have only 10 left, and the elements left in the binary tree 1 is 12. So 12 is actually greater than 10, so we cannot put it inside our stack. So we are going to simply pop 10 and add it to our result. And our stack 1 is empty and we have one element left, so let's put that on top of our stack. We don't have elements to compare, so let's put 12 to our list, and thus our list is sorted. So what is the advantage of using this? The first thing is the values in the stack cannot exceed more than 3 for this example, because it is a binary search tree. So the values in the left side will be always lesser and the values in the right side will be always greater. So at any point of time, the maximum value a stack can hold is height of the tree. Because if the value goes deeper to the last leaf node, the possible value the stack can hold will be that 4 or 3. And that same applies to the right side of the tree, and same that case will be applicable to the binary tree too also. So the height of the stack will always be, sorry, the maximum numbers that we put in a stack will always be equal to height of the binary tree one. So let's say height 1 will be the maximum number of elements that we put into stack, and height 2 will be the maximum number of elements we put into stack 2. So in this case, we only use h1 time to put the values and pop the values in stack 1. Same way, big O of h2 time to put the values and pop the values from stack 2. And other comparisons and popping the values from the top of the stack will always take big O of 1 time. So we simply take the value and put it in an array in, again, big O of 1 time. So overall, this algorithm is going to take big O of h1 plus h2 time, where h1 and h2 are the heights of the given binary tree. So hope I made some sense to this algorithm. So let's go to the code now. So yes, as I said, we are going to have two stacks and a list to add our results, because our return type is list of integers. So which is what we are going to return finally. So as I said, we are going to iterate both the trees and do in order traversal. So yes, as I said, we are going to iterate the array till it meets null, and we are going to push the values into root stack 1 and stack 2. So now, as I said, we are going to compare both the stacks and then go again to add the rest of the values. So we are here checking if our stack 1 is not empty, and then we peek the value from stack 1 as well as stack 2 and compare. If stack 1 is less, then we are going to pop the value and add the result, and we are going to iterate the further side of the root 1. If not, if it is the other way around, then we are going to pop the value from stack 2 and add the value to the stack 2, and then choose to traverse the right side of our route 2. Yes, this is it. The loop goes until all our nodes are visited, and finally we are going to return our result. Let's give it a try. Yes, so let's submit. Yes, our solution is accepted and it runs in 14 milliseconds. So thanks for watching the video. Hope you like this video. If you like this video, hit like, subscribe, and let me know in comments. Thank you.